Welcome to Statics. We'll begin our discussion by introducing a few basic concepts along with the units we'll use to describe physical quantities. One of the distinctions we'll frequently make is whether to treat an object as a particle or a body. A particle is an object that can be treated as a zero-dimensional entity, but there are additional implications that may not be so obvious. Even though a particle is zero-dimensional, I'll begin by drawing a dot on the screen so we have something to see. I could view the particle from this perspective, or this perspective, or this perspective, or any other perspective, and there is nothing about the particle that enables me to distinguish where I am around it. Conversely, I could hold my position fixed and rotate the particle about some axis, but lacking size, there is nothing to indicate that the particle has actually experienced a rotation. The significance of this is that restraining a particle against motion amounts to ensuring an absence of translation. The concept of rotation is meaningless. In this case, equilibrium is imposed if we require the sum of all forces acting on the particle to equal zero. We will write this as a vector expression, sum of forces equals zero. And we should interpret this equation as imposing an absence of translation in all directions, or imposing translational equilibrium, also called force equilibrium. In many problems, we'll be given an object that certainly doesn't look like a particle in that it has size. Consider this sketch showing an object that clearly has a height and a width sitting on a surface. When should we treat this as a particle, and when should we treat it as a body? From a problem-solving perspective, we're looking for the actual dimensions to be given. If dimensions are given, we'll treat it as a body, and this requires an additional set of equations beyond force equilibrium to ensure total equilibrium. If no dimensions are given, we'll interpret this as instructions to treat the object as a particle, and equilibrium will consist entirely of force equilibrium. In contrast, a body is an assembly of particles amounting to significant size. The designation of size as significant depends on the eccentricity of forces applied to the body relative to its center. The presence of such eccentric forces tends to impart rotation in addition to translation, and constraining a body against rotations requires an additional set of equilibrium equations to supplement force equilibrium. Here we have the same object shown earlier with a height and width explicitly given. Suppose this object represents a piece of furniture that you are moving around your dorm room or apartment. It will have a center of some kind, and we'll indicate that by putting a dot in the center of the furniture, and we're going to give that a label G, which we will later call a center of gravity. When we consider the eccentricity of forces, we are looking at their position relative to this center. Suppose you're trying to move this furniture around your living space now, and you exert a force on the object as you try to push it around. I'll designate that as a force P for push. As we'll see in Chapter 2, the force has a line of action that is coincident with the arrow that I've drawn. And it's obvious that there is a distance between this line of action and the center of the furniture at G. I'll indicate a position vector R as beginning at G and going to somewhere on the line of action of this pushing force P. The object also has a weight, and I'll indicate that pointing down. And the weight, as it turns out, acts at the center of gravity. So the weight will be one force that has no eccentricity with respect to the center of the object. Since this object is sitting on a floor, there is a distribution of force underneath it that represents the floor's reaction to the presence of this object. I'll designate this force as N, a normal force, since it is perpendicular or normal to the floor's surface. It isn't guaranteed that N goes through the object's center, so I'll show it as slightly off-center from G, and again, its line of action will not pass through G. The floor also offers some resistance to the object sliding over it in the form of friction. That is tangent to the floor's surface, and I'll indicate that in the sketch with the label F. The line of action of F is parallel to the floor, so again, it doesn't go through G and also has an eccentricity with respect to G. The sketch shows 4 forces acting on the furniture as you try to push it around your room. The forces P, F, and N are all eccentric in that their lines of action don't pass through the center of the furniture at G. Each of these forces will tend to impart a rotation about G in addition to a translation, and the extent to which they tend to impart rotation will depend on both the magnitude of the force and the magnitude of the eccentricity. If the piece of furniture is an ottoman, it is short and squat with width much greater than height, and you probably don't have to worry about overturning it as you wrestle it around the room. If it's a chest of drawers or bookcase with the height larger than the width, then you have to be careful moving it in that you don't tip it over. If the object is in equilibrium, we have to impose 2 sets of conditions corresponding to equilibrium against rotation as well as translation. This gives us a set of body equilibrium equations. Which will still consist of a balance in forces, which is equivalent to imposing translational equilibrium, and in addition, a sum of something called moments, often about the center of gravity, but not always, that has to equal 0, that amounts to imposing rotational equilibrium. The quantity m is called the moment of the force and depends on both the force and its eccentricity, as indicated, for example, by the position vector r from G to pushing force P in the figure. When we write these equations, you should be thinking of force equilibrium as equivalent to translational equilibrium and moment equilibrium as equivalent to rotational equilibrium. Before continuing, we can use this figure as a summary for all the topics we're going to consider as we move through this course. I've written these force and moment equilibrium equations as vector equations, but we obviously haven't talked yet about vectors or how to perform mathematical operations with them. Chapter 2 will be devoted entirely to vector mechanics. In Chapter 3, we'll discuss particle, that is, force equilibrium, and introduce a few important mechanical elements along the way. In Chapter 4, we'll discuss moments of forces, that is, how to find the m in the moment equilibrium equation given the position and force vectors. Then we'll be prepared to impose force and moment equilibrium on an individual body, which we'll do in Chapter 5. In many instances, we're not just interested in single bodies, but in assemblies of bodies, as in simple tools or machine elements. In Chapter 6, we'll consider equilibrium and force transmission in assemblies of bodies. We'll look at stationary objects like bridges, but also consider temporary, static configurations of assemblies such as machine elements, earth-moving equipment, and prosthetic limbs. In this way, our first 6 chapters will all have a common theme, moving from simple to more complicated impositions of equilibrium, from 2D particle problems to 3D assembly problems. The last 4 chapters will clean up details omitted in the first 6 and provide some foreshadowing of topics to be considered in subsequent mechanics courses. In Chapter 7, we'll address the issue of centers of distributed forces. In the case of our piece of furniture, I've sketched a center labeled G for center of gravity. The object obviously consists of distributed mass, and if the object has a simple geometry and the mass density is uniform, then I can put G right in the geometric center of the object and be confident that reflects the center of gravity. But what do I do if the geometry isn't simple and the mass density isn't uniform? How does G change if I'm trying to wrestle the furniture around the room with some drawers full and others empty? Along a similar line, if I'm exerting a push through P, that's going to tend to lift the object off the ground and reduce the pressure between the object and floor near P and increase the pressure away from P. The normal force N represents the integrated sum of this pressure over the floor to find a total or resultant force, and the fact that it's off-center is indicative of the pushing force tending to cause this change in distributed load at the floor. How do we find the center of N in a case like this? Chapter 8 will deal with internal forces, a subject that will have greatest relevance for slender structural elements used in construction. This will be especially important for those of you intending to become civil engineers. This is perhaps the one topic that doesn't have a direct connection to our furniture illustration. In Chapter 9, we'll consider the nature of friction. How should we represent this frictional force F sketched in our illustration? On what physical quantities does it depend? Finally, in Chapter 10, we'll consider a mysterious-sounding topic called moments of inertia. There will be 2 separate kinds of these moments, but in our present illustration, we are especially interested in the resistance a body offers to rotational motion. This is quantified through something called a mass moment of inertia. If we push too hard and the furniture begins to tip over, how fast does it acquire angular motion? The mass moment of inertia allows us to quantify this. In short, we can see elements of almost all the topics we'll cover throughout this course in this one simple furniture illustration. Finally, before we introduce some additional concepts, we make a distinction between rigid bodies and deformable bodies. Anything made out of a real material is deformable, but sometimes the deformation is so modest that we can model the body as though it were infinitely stiff or rigid. A fishing pole is an example of a body that must be treated as deformable. It clearly is designed to be hyperflexible, and its geometry changes markedly when there's a fish on the line. In contrast, many commercial buildings are assembled over a skeleton of steel I-beams. Steel is such a stiff material, and I-beams are so substantial, that the deformations that accompany even significant loads are often minuscule. So with the exception of certain special mechanical elements, we will consider bodies as rigid, meaning the exertion of force in the body does not change its geometry in an observable way. In addition to making a distinction between particles and bodies, we will make a distinction between scalars and vectors. A scalar is a physical quantity characterized by a single number. A scalar has a magnitude but no directional orientation. We observe that an unrestrained body struck with a single, consistent, repeatable force is launched with the same initial speed, collinear with the line of action of the applied force, no matter what direction the force is applied. For a force of specified magnitude, the initial speed depends on the particle's mass. Mass represents the resistance a body offers to acquiring linear or translational motion, and it is independent of the direction of the applied force. On this basis, mass is a scalar. A vector is a physical quantity characterized by both magnitude and direction. When a mass is in the presence of a gravitational field, a force is exerted on the mass and its direction is aligned with gravity's direction. We refer to this force as the body's weight. If the body being struck is a ball on Earth, it follows a parabolic trajectory back towards the Earth. The mass may be a scalar, but its weight is a vector. Because vectors have both magnitude and direction, we will show that we can generally write them as a vector F equals a magnitude on a direction. We read this representation as vector F has magnitude F along orientation U. We have partitioned a vector into a product of magnitude on orientation. We will see that position, velocity, which is the time rate of change of position, and acceleration, which is the time rate of change of velocity, are all vectors. We could define a position vector between the goalposts in Camp Randall Stadium as position vector r equals scalar length on direction u. If we were defining the position of the north goalpost relative to the south goalpost, u would be a pointer oriented north. If the other way around, u would be a pointer oriented south. The magnitude of the position vector is its length. In the case of our goalpost illustration, it would be a little over 120 yards. This last example illustrates that vectors and scalars are related. We will always refer to position as a vector because the location of one object relative to another requires specification of distance and orientation. Because we will always be able to write a vector as a product of magnitude on orientation, a scalar is the magnitude of a vector. Length is the scalar magnitude of the position vector. Even though the words length and position are similar, one indicates a magnitude and the other conveys orientation in addition to magnitude. The basis for mechanics is Newton's laws of motion. It is important to remember that these laws are formulated from observation. They are not derived from more fundamental physical principles. They represent our starting point to understand the relationship between forces and motion. The first law states that a particle subjected to no net force experiences zero acceleration. In most of our applications, this refers to a particle being stationary, but it is possible for a particle to be moving and not accelerating. We will elaborate on this condition shortly. The second law provides a quantitative relationship between net force and motion. It states that the acceleration experienced by a particle subjected to a net force is aligned with that force and inversely proportional to the mass, a scalar. For a specified force, an object with little mass offers little resistance to acquiring motion and accelerates quickly. An object with more mass offers more resistance and accelerates comparatively slowly. The third law is one of equal and opposite reaction. It states that forces between interacting bodies are equal in magnitude, opposite in direction, and collinear. It should be mentioned that the first and second laws apply to particles, but because bodies are assemblies of particles, it is possible to formulate equations of motion for bodies from those for particles by summing over all particles constituting the body. When we do this, we find a distinction between the governing equation for a particle and the corresponding equation for a body. The distinction is, for a particle, we have the equation that's shown here, which is simply F equals ma, or sum of all the forces acting on the particle equals mass times acceleration. And for a body, the governing equation is sum of all the forces equals mass times the acceleration of the center of gravity. The equation describing the linear motion of the body looks just like that for a particle, except the acceleration refers specifically to the acceleration of the center of gravity. So for instance, looking back on our illustration with the furniture, we would be looking specifically at the acceleration of the material point at g that's labeled in that figure. Because a body's motion is generally a superposition of translation and rotation, every material point in the body generally experiences a different acceleration. This body equation tells us that we can ignore all those different accelerations and just focus on the acceleration of a single material point, that coinciding with the center of gravity. In this way, body motion appears similar to particle motion. In the case of static equilibrium, the acceleration of the particle or the body is zero, and the right-hand side of either equation becomes zero. Force equilibrium for either the particle or the body looks the same, which is that the net force is zero, or the sum of all forces acting on either the particle or the body is zero. Before going further, we take a moment to elaborate on what it means for a particle to experience no acceleration. Velocity is the time rate of change of position, and we could write that as v equals time rate of change of position, which we could also write as a magnitude of the velocity vector on its orientation. Here we have written the velocity vector as the product of its scalar magnitude, called the speed, on an orientation. Since the acceleration is the time rate of change of the velocity, we could use the product rule from calculus to write the acceleration as shown here. This tells us that acceleration can occur from a change in speed at constant orientation, the first term, or from change in orientation at constant speed, the second term, or from some combination of the two. The acceleration is obviously zero if the particle is stationary, but it can also be zero if the particle is moving in a straight line at constant speed. If the speed is constant, the first term is zero, and if the orientation is constant, that is, it's moving in a straight line, the second term is zero. Therefore, it is possible for a particle to be moving and not be accelerating, although the motion involved is very simple, namely moving at constant speed in a straight line. In most of our applications, we will be looking at stationary objects, and it is obvious there is no acceleration. Every once in a while, though, we'll encounter a problem where there is motion, and yet the equations of static equilibrium are still valid, because simple motions can be consistent with an absence of acceleration.